Okay. Schrödinger did not say anything about metabolism, right? He said something about order, avoiding decaying kind of things. I'm not sure. Okay. Topic 11. 생각들 잘 안 해봤나 봐. 절반은 써보물 안 보자네. Single layer. Okay, let's see. 민주주의랑 1번이 답이네. Okay, still single layer. Okay. Okay. Okay, carbohydrate, 90% correct answer, one wrong answer, and one no response. Okay, let's go. Okay, you guys have studied the origin of life. How come you guys look a little tired today? 점심 먹고 와서 그런가? Let's try to stretch a little. Move your facial muscle too. Okay, let's go. Okay, the topic of this week was the origin of life and some of the form of the ancient the model of life. We don't know exactly how our life started, whether there was really God that touched there or not. That's difficult to prove, so we try to make some scientific model. And then the question was what is life? And there's several different kinds of definitions. If it's difficult to define right away, then you can start with some basic component. Material of life, molecule of life. Molecule of life, we can say as organic molecules. Organic, that word came from organism. Organism means it's living things. So organic molecule is defined originally some molecule which is generated by life. So that's why, in terms of the definition, molecule of life can be organic life, we can think. So organic molecules going too fast. So to check, you already know, so we already have said the carbon is the basis molecule of an organic molecule. Well, how carbon is selected is something good to think. Anybody knows what is the most abundant element on Earth? Not in Earth, on Earth, on the surface of Earth. You already seen the answer. Oxygen. Where is that oxygen? Maybe you may say in the water, sea water, but the sea layer, so deepest one we found is only 10 kilometer. Radius of the Earth is 6,400 kilometer. So 10 kilometer, so 1 out of 640, it's a very, very thin layer. So oxygen amount in water is almost nothing. Why does it move so fast? Maybe I put something wrong here. Okay. Okay, that oxygen is not in water, but element-wise, weight percent-wise, it's almost a half of all the elements. It's an amazingly high number. And second, the abundant element is silicon. Silicon occupies almost 30%. So almost 80% of those materials are silicon and oxygen. Those are the composition of silicon oxide. Those are main component of stones. Okay, so they are the main material on Earth, highest are the abundant materials. In comparison, the carbon, the center molecule, center element of life, the organic molecules, surprisingly, that amount is only 0.2%. It's 1% of a silicon amount. It's a little funny to see this. Silicon and carbon, they are in the same family in periodic table. They have 4 arms, they can make a bond to each other, they can grow those chains. So if all other conditions are equivalent or similar, maybe this element could be chosen as the basic material of life. Or at least we should have competitor. Silicon-based life versus carbon-based life. Some of you may say, oh, we have a silicon-based life, computers, computer virus, AIs, but they are not silicon oxide, they are pure silicons, impure silicon, right? So some doped silicon, but they are not silicon oxide. There's a good reason. Chemically speaking, silicon-silicon bond is 50 kilocalorie per mole. That's the strength or the stability. Carbon-carbon is almost double the strength. So this energy is similar to pi bond dissociation energy. This is a sigma bond. So that means pi bond, by giving a little short wavelength of light, we can break it. Means under the sun conditions, sunlight can break this bond. So that means under the sun, maybe silicon-based life, they cannot survive. Maybe they go into the cave, maybe under the sea, maybe at very low temperature, they may survive. If not, at least they don't compete with us. On Earth, we live. They live maybe deep inside, dark area, maybe. Anyway, so carbon is the basic material of life. And then some of those the life, the molecules, organic molecules, representative, some of them, let's look at carbohydrates. First product of photosynthesis, carbohydrate. 이것도 이렇게 보여주면 안 되는데. 왜 이러지? 뭐가 이상해졌네. Okay, carbohydrate. So this is photosynthetic, the process is here. Carbohydrate here, first product is a glucose. If you draw this formula, there is a molecular formula. If you draw that in a simplified version, isn't it? It's like this. So if we did not know the exact molecular formula, maybe experimentally we can get that formula. And if you look at that formula, this formula, carbon plus water. Name of this class of molecules, carbohydrate. It implies original discovery of experimental formula, carbohydrate. Means hydrated carbon is carbohydrate. And that formula exactly represents that concept. That is composed of 6 carbon. 5 carbon carbohydrate like ribose. Exactly the same formula with the 5. That's a C5H10O5, ribose. That's also carbohydrate. Perfect definition, right? That kind of discovery was made more than a century ago, even before 20th century. 19th century, the organic chemists at the moment, maybe they were much more skillful than us. They didn't have an NMR, normal research. They had only the tools of distillation, extraction, recrystallization, and then get those crystal powder, and then analyze the relative amount of carbon and hydrogen and oxygen, and they found this formula. They were very excited. Oh, carbohydrate is, we just need here carbon and water, and then give some magic catalyst. Philosopher's stone, maybe 200 to 300 years ago, that could be the catalyst for alchemy to make a gold out of something. But maybe at the moment they felt we are modern organic chemists. Now we learned the formula of carbohydrate, basic food material. We need to culture, but actually don't need. If you have a coal, the carbon source, and add water and some recipe, if you cook, then we can make glucose. That is cutting edge knowledge at the moment. They knew the composition of carbohydrate. So now we know that this molecule may have thousands of different isomers. Structural isomer, residual isomer, and stereoisomers. Glucose is the one specific form out of it, and very complicated material too. So based on this, now let's say the photosynthesis. Now this question I gave you, and then some of you gave very standard answers. It's divided by 2 parts: dark photosynthesis, the light photosynthesis first, light capturing, and then capturing that energy, utilize that for the second step, dark reactions, blah blah blah. And then there is ATP, NADPH is made as an energy source, and then utilizing them and eventually synthesize the glucose. Yeah, good answer. My question was, this was my key question. What is the carrier of energy? Maybe NADPH, ATP, yes, they are kind of battery molecules. Energy stored, biological batteries. It's a good answer, but that's not the first one. I wanted to hear something else. And some of your other friends gave this kind of picture. Maybe some kind of picture may be better. Is this a handwriting? Okay. So he drew this, and then he tried to explain something even without any word. Good, right? But still, I wanted to see something happening here. Let's say we are talking about life forms in terms of a cell. So let's say this is a cell, and there is a membrane. Many of you believe that this is single membrane, single layer. Let's see. And something happens on this membrane. Actually, the membrane, okay, this is the chloroplast, so this membrane. On the surface of here, something goes on. And in the last minute, I prepared the lecture note and then packing up, and I just checked one more time, and there was a new answer there. This is what I want to do here. The first event, what happens on this membrane? This is the lipid bilayer membrane, and there is another bilayer like this, similar to mitochondria. Mitochondria, we believe, originally there was a separate bacteria, and then it was engulfed by bigger cell, and then they live together, symbiosis, help each other. Similar things, chloroplast, we also believe this was also another bacteria, and it was uptaken by the cells. And that means they have their own membrane too. So on their membrane, again, lipid bilayer, 2 layer, they have some machineries here, photosynthetic machineries. First thing, energy source was the sunlight in the form of a photon, light energy coming through, which captures that light is this. Molecules are composed, especially organic molecules, they are composed of carbon-based molecules. They do have a reaction, and that reaction is done by electron movement all the time, not nucleus collision or nucleus reactions. Of course, nucleus is also moving, but that just carries electrons. Real reaction happens only through electrons actions. Now, the action here is, you guys have learned something about molecular orbital or atomic orbital kind of things. There is some machineries here. Their machineries capture this light. Light usually we write this way, h mu. This light is captured. How? This electron is jumping to higher energy, and then that keep that light energy into these molecules. Light absorption through those kind of dye molecules. Because I said dye because this light mainly, sunlight's main, the center wavelength is a yellow or green light. And their light is captured by this light absorbing material. This event is the first. And this electron is so-called excited electron or hard electron. And this energy is quite a valuable energy, quite high amount of energy. And they don't want to waste this. This is very hot because of that high energy. And this energy is not, they don't want to waste it or use up using making only one ATP. And they carry over to different molecules. And step by step, jumping down to another energy level like this. And then every step they generate new materials, energy stored materials. There, the first product is NADH, NADPH, and eventually NADPH is a bigger. One NADPH can make a 3 ATP. So that's big battery. ATP is a small battery. And then usually carrying on those energies and make stored carryable small batteries. So first event was this kind of light capturing machineries. Those are stacked inside this chloroplast in the unit material. So everything, if you say you learn chemistry, means you learn about electrons reactions. Very fundamental reaction in life. Photosynthesis is the very sophisticated but very first step of utilizing the outside of the energy imported into life or the world. That happens through this excitation of electron. That is the first event. Okay. That one I wanted to hear. This answer was given by Jayon. Jayon? I think you deserve 1 point. Okay, so anyway, I almost missed this. Just in case I checked one more time the last 10 minutes before, so that's why this page is not in your notebook. Okay, carbohydrate structure. Looks like a very simple formula like this, but this is only one form of a carbohydrate, so-called glucose. 6 carbon, and then depending on how you draw, it can be drawn this way, or this format, or this kind of a little more realistic shape of the chair conformation, or maybe this format. All of them is the same molecule, but with a different notations. Depending on how you want to describe, you can choose which form, which structure you want to use. Carbohydrates is the first molecule. Utilizing those molecules, now we make other biomolecules. You may have heard the basic 3 biomolecules, I guess. Carbohydrate is one of them. What are the other? amino acids or the proteins, so they are same, and lipid molecules. Okay, let's look at amino acid first. Amino acid is the component of proteins. Amino acid, this is the basic structure of amino acid. Now, by looking at those structure, you can see there is amino, and you see acid, carboxyl acid, and connected through one carbon. So one carbon, so this position next to acid, we call this alpha position. If you have one more extended, then alpha, beta, gamma, delta connected positions. So amino acids, the name of amino acids already implies the structure of the molecules. Carbohydrate, we already said it here, right? Carbohydrate. By the way, if it's composed only with a carbon and hydrogen, that kind of molecule, what do you call? Carbohydrate. Hydrate, carbohydrate is this is a hydrate. Carbohydrogen, 뜻은 알겠지만 hydrocarbon. Okay. Hydrocarbons, the hydro is a hydrogen. CH, only with the CH, those molecules we call hydrocarbon. That is the material in crude oil. Most likely crude oil is also produced by lipoforms. It's also organic molecule accumulated, and somehow they lost oxygen, nitrogen, or other materials, and just condensed into the hydrocarbon form. So that hydro is a hydrogen. Okay. Now amino acid, it implies that the structure, should have one amino group, one acid group. And there may be many options, but anyway, utilizing these two functional groups, utilizing one carboxylate and one amino group, they can make a coupling. And then this way, and then by using one molecule of water. By removing one water, so it's kind of condensed, so this reaction we call condensation reaction. Means making coupling by removing one molecule of water, dehydration reaction. And then it can go further and further. So amino acid can be connected to each other like the Lego molecules. So if you look at this, the carbohydrate structure, now one amino, one carboxylate, and this position one carbon. Now you have an option of many different kinds of structure here. There can be hundreds of thousands of different kinds of functional groups you can add. But in nature, we didn't use many Lego blocks. We chose 20 main structures. Everything has amino acid structure, alpha amino acid, but with different structures like this. Now, if you want to make, very big diversity, protein is the main molecule which should do every functional thing in our body. Catalyst, building blocks, and it should do almost everything. Then you may want to cover all the chemical properties. I said all the chemical property. What kind of chemical property do you know? Different chemical property. What can you say? Okay, in the molecular size, interaction of those materials, out of 4 basic forces in nature, strong, weak, nuclear force is out of question. We don't touch nucleus, right? And gravity is a too big scale, and that small are the molecules. They don't feel gravity or ignorable. So only left over thing is electromagnetic force. Electric structure is the origin of every molecular interactions. Then, in this case, if you choose different side group here, then your option may be, I want to have a positive charge. Then there are, at least we have 2 positive charged amino acid here. I want to have maybe negative charge. There we have also 2 amino acid which has negative charges. Out of 20, 2 positive, 2 negative. And maybe I want to have a hydrophilic, hydrophobic. In other terms, polar, non-polar. That's what we call hydrophilic and hydrophobic. kind of things. That kind of options are here. This is our choice. The life forms on Earth, 99%, 9% of the life forms on Earth, we utilize only these 20 building blocks. That does not mean that these are perfect sets, just that this is maybe arbitrarily chosen, but reasonably diverse structures. So that's our basic the amino acids. If there's another life forms in Mars, they may use different kind of amino acids, possibly, very possible. Okay, utilizing this, they can be connected to each other. One amino acid, one amino, and one other carboxyl acid, they can be connected to each other. So first product they can make is a linear polymer, like this. So one position, amino position, the other position may be carboxyl acid position. By notation, usually we count from N-terminal to C-terminal. Okay. And one amino acid each, and they can be connected. Sometimes they can be cross-linked through this system motif. Where is it? Here. SH bond, they can make a SS bond by oxidation. They can cross-link to each other. So linear protein, second linear protein, they can be connected to specific positions. They can make three-dimensional structure and four-dimensional structure kind of things. So this is basic structure of proteins. We do not go too much details, but we covered two basic biomolecules, carbohydrate and amino acids. Okay. Next one is lipids. Lipids, what is the definition of lipids? Carbohydrate, with the name, we could see those structure. Amino acid, we could understand. Which amino acid, we don't know, but at least by looking at that, okay, this is amino acid, we can say. Lipid, what is lipid? Show me example. Okay, here's the example. All of them are lipids. Some lipids looks like fatty acid with a long hydrocarbon chain, and the position is acid. With a little difference of double bond here and there, but anyway, this is fatty acid, what we call. But how about this? This is steroid molecule, cholesterol, and structurally they do not look similar. And still we call all of them as a lipid. Then how do you define lipid?
Soluble to organic solvent.
Yeah, whether the molecule is soluble in organic solvent or not, that is the definition of lipid. In other terms, fat is a lipid. It's a little funny, but that is the definition of lipid molecules found in liposomes. Okay. Now, utilizing this, now let's think. So this is typical structure of fatty acid. Crude oil material, hydrocarbon, they have only this part, they do not have this. Right? It's just a simple long chain of hydrocarbons. They have a lot of energy there, stored energy. Maybe it's captured long time ago by the sunlight, captured that energy, connect those carbons, and a lot of energy there. That's why if you burn it, then it generates a lot of heat. That stored a lot of energy. If you can eat it, then it can be good energy source. Unfortunately, we cannot eat it because that's too hydrophobic. That is the definition of a lipid. At least we need to have some handles, like at one end, acid or alcohol, we need to have that kind of a functional group. Then we can take it. We love this, don't we? It's a greasy materials, fatty acids, smells good, tastes good, right? Once we have this small functional group like carboxyl acid, now we can eat it, we can utilize. That's a part of live biomolecules. And if you keep them together, now funny thing we can find, now according to the Sostek's definition, what's the first form of now there's some answers like this. Maybe fatty acids, we need to have a boundary of life. Boundary of life, inside and outside we should distinguish. And then fatty acid may be the component, possibly, because fatty acid could be formed abiotically too. Now if you have a multiple fatty acid, and this is the hydrophobic part, this is the hydrophilic part. Hydrophilic part, they attract they attract to each other. And hydrophobic part, they do too. If this is in aqueous environment, water environment, water is hydrophilic. The definition of hydrophilic means like water, right? So water is the origin of hydrophilic. So in water, then this part is heavy, this part is not heavy. That's why if you mix them together, the fatty acid in water, they want to hide this part inside hydrophobic area and expose only hydrophilic area to the outside. This is also entropy involved assembly, self-assembly. And if they go on like this, two possibilities. Same molecule, let's say, fatty acids. It's one part hydrophilic, one part hydrophilic. In water conditions, they hide this part inside and express their polar group or hydrophilic group to the outside. If there is opposite way, oil environment, organic solvent environment, then they behave opposite way. They keep this head group, polar group inside and expose this hydrophobic group to the outside. So this may happen. Now, let's say this is no space here, then this kind of the structure we call micelle. Only surface is there, that's kind of just a drop it. So in water, they form like this. In oil, they form like this. Now, if this chain is getting longer, now there is a possibility that this is for the small fatty acids, they just form micelle. But if this chain becomes longer, now they have a chance to form two separate space. Let's say this is a water condition. Then inside is also water, outside is also water. And those boundary of the material, this can be bipolar material like this. Hydrophilic head group facing outside and also inside. And then middle side here, this is hydrophobic area. This kind of a segregation is possible. Now we have some kind of a boundary which can separate inside and outside. We can choose outside as a life, inside as an environment. But here, the environment is very small, life is too big outside, it's more difficult to control it. So maybe it's easier to keep, okay, this one is something we wanted to keep, or maybe we want to define that's me or life. If they can reproduce, they can sustain, they can exist for a long time, then there is something special character evolves. So Professor Jostek suggested that maybe ancient time, this kind of a fatty acid, and maybe in water. Which water? Seawater. At the moment, the seawater should be most abundant water source. In seawater, and if there is any fatty acids component there, they could form this kind of vesicle structure. They could form this kind of structure we call liposome. And let's compare this with soap bubble. Soap bubble, most of those the primary soap is also composed of sodium fatty acid. It's the same fatty acid with just a salt. Now, comparing to this in water, same material, if you put those soap in water, exactly they will form this. Okay, pilumul, soap in water, they will form this kind of liposome. Now we supply third phase. By blowing it, we supply water, oil is a two phase here. Oil very thin oil layer, and inside outside those are aqueous layer, aqueous phase. Now we provide third air phase. So this bubble is now moved out, inside, outside. Both of them are air. I said the third, then what happened to the water? We have fatty acid here, and water actually very thin water layer is there. Now, let's think. Air is hydrophobic or hydrophilic? What do you think? Phobic? Philic? To be hydrophilic, you need to have a kind of a charge separated status, right? Hydrophobic, in other terms, they call polar. Polar means charge plus minus is separated. That's a polar. In air, it's almost an insulator. Right? Then, relatively, you could assume air may be hydrophobic. Then, it's like behave like an oil area. Then, the structure may be something like this. Air outside, air inside in the bubble, and then facing this tail outside, tail inside, and there is a small layer of water in between. 3 layers. Air, lipid, water, lipid, air kind of structures. This is the bubble membrane structure. Now it forms this kind of a bubble, and then slowly this water is somehow snake out, and this membrane is not perfect. In some terms, we said that membrane segregated out inside and outside, but that membrane is not very strong membrane. Sometimes there's a little leak in and out, and the water can be slowly evaporated. And then getting thinner and thinner, and then once they cross-bury each other, negatively charge it, negatively charge it, they come close, what happens? They expel to each other, and they can break up. Okay. So when I asked you the structure of the cell membrane and soft bubble, some of you said, okay, proteins and soft does not have a protein and not selective glucose. Actually, this is not what I wanted to hear too much. Of course, soft does not have a protein on it. Cell membrane has some kind of proteins on it. And a little more question like this, a little more general structure I wanted to hear like this. And here, okay, some of you said, oh, I had some difficulties to follow the idea of why the permeability has a problem, polar and polar kind of issues. Okay, then when I give these questions, number 4 of your assignment material, some of you said there is hydrophilic small molecule is easier to enter through the membrane. Hydrophilic, do you agree? Hydrophilic molecule prefers to penetrate to the membrane. Okay, let's vote. Hydrophilic prefers. 2 options. Hydrophilic, hydrophobic. Hydrophilic prefers. Hydrophobic. Let's see. In the membrane, so in water conditions, outside, inside, hydrophilic. Membrane inside here, these are hydrophobic, right? If you put very hydrophobic material there, like a cholesterol, then those cholesterol molecules, they are also hydrophobic. If they can penetrate this thin layer, they may prefer to go in and stay here. They don't want to move out. Cholesterol is lipid. Lipid likes organic, the hydrophobic area, and if there is options, then they prefer to reside in the membrane. Hydrophilic molecule. Now this is captured inside here, but if this is outside here, they come close, and then interact maybe around here, but they may have very difficulties to penetrate this layer. They cannot go in and out. Then which molecule is better? In between. A little hydrophobic, a little hydrophilic. Then they can come here, and then in and out, and then one of them is going. And those kind of molecules, sometimes, in many cases, it's difficult to have. That's why, in many cases, we need to have a helper, like the proteins, protein transporters. This membrane, in principle, hydrophobic molecule, they can be captured on the membrane. Hydrophilic molecule, they cannot penetrate. Even water molecule, they cannot penetrate. So even for water molecule, we need to have this kind of a channel or pump which can capture water molecule and put inside or put outside. So-called the aquaporin, kind of a transporter protein we need. If not, even with the water, inside the water, we will die of thirsty because we cannot take the water in. So this is the kind of a situation. Exceptional case is, it's like intermediate molecule. Perfect example is ethanol. Ethanol molecule has a 2 carbon, 1 hydroxy group, very small. This 2 carbon has a little penetration here. Hydroxyl group is more preferred here. So it's not fully going in, but relatively it has a good chance to penetrate. And it can make, some of them may reside inside here too, with a OH here, 2 carbon here. So they make the whole membranes loose. Our cell membranes should be tight, and then you can have good the sensory system. Now if you take a lot of the drink, then it becomes loose, right? Membrane becomes loose. That's kind of a feeling we can get. So that kind of molecule is maybe passively in and out. But most of the molecules, they need a special structure like this. Okay. Maybe ancient cells, they utilize very simple form of fatty acid, but modern life forms, modern cell membrane, actually they have, instead of 1 tail, they have 2 tails. And then the header group, they want to have an even stronger polar group, phosphate group, which has 2 charges, 2 minus. So compared to fatty acid has a carboxylate, 1 minus, and weak acid. Phosphoric acid is a stronger acid, 2 negative charges, and 2 tails make this membrane more segregating, more solid boundary. So this is the current advanced lipoform cell membrane structure. 2 tail and phosphate group. That's why this kind of lipid we call phospholipid. Again, this phospholipid also needed to have a bilayer. One side they should face aqueous, and the other side another aqueous. This may be inside, this may be outside. This is the boundary of life in cellular level. Okay. Now, if everything goes well, then there is some space inside. This is environmental space. Now, if we can accumulate some material inside here, like you have seen, maybe polymerized material cannot go out, they can start to accumulate some kind of identity. And if they acquire the ability of replicate, self-copy, then that could be some good model of starting of life. There is Professor Josek's the video says. Okay, I gave you this question too. What is the thickness of the biological membrane? It's not full answer, but there is some clues was given here. It's a good calculation. If you look at those membrane here, now you can count those carbon number of this tail. Approximately those are around 20 carbon and 2 layers. Then this is a good guess, about 40 something. Then you can calculate those lengths. Right? What is the length of one carbon-carbon bond? Hmm? 0.1 nanometer, actually 0.15 nanometer, 1.5 angstrom. That's good range. 0.15 nanometer. This is 1 carbon-carbon length. And this carbon is connected this way. They are not like this, right? They are zigzag shape. Then this is a 0.5, the approximately 1 unit over here. You can say this is approximately 0.1 nanometer, right? This is a 1.5, but this one is a little shorter than this. So about 40 carbon, that gives you a number of thickness of the membrane is what? The exact number we don't need. 4 nanometer or 4-5 nanometer. That is a membrane thickness, 4-5 nanometer. I will come back to this if we have more time later. So that's about approximate membrane thickness. Our cell is about 10 micrometer size. 10 micrometer, 1 micrometer is 1,000 nanometer. Membrane is 4 nanometer. That kind of a ratio you can keep in mind. Okay, so that's membrane structure. And this guy is Schrödinger, and he said about the definition of life in terms of entropy. If everything is organized inside and keeping that entropy as low as possible, self-maintaining, and can go long, then maybe that could be, physically speaking, that could be good definition of life, he said. And sometimes we hear egg first or chicken first, kind of a paradox. Scientifically, that's super easy, right? Single cell and many cells. Of course, we should start with some kind of single cell first, and it developed into the multicellular structure. And but if you look at this, the single cell, whether can we say this is boundary of life? We just said that membrane is the boundary of life. Now this one is not membrane; it's a kind of a solid barrier. But there is inside there's maybe membrane. Now by looking at this, from which stage is this life? This is life, looks like. Then which is the boundary of life? Kind of questions. So it's not easy to define life. And even if the embryo is growing, then from which stage? Week 1 or week 2, do we count this as a human? It's not easy. If we just keep going, let it keep going, then yes, it will become human later. But before 10 weeks, after 10 weeks, from which line we should define this as a human or life? It's not very easy questions. So, putting aside that question, we said in cell level, we said this is inside, outside. It looks like a straightforward. Is that really straightforward? By looking at our body, which part is inside? Let's say inside the stomach. Is that inside or outside? Topologically, that should be outside, right? Starting from here, going through the other end. Okay, topologically, we are like a donut shape, right? Inside the donut, we don't count that as inside. We should make a punch here and then go in. Maybe that's inside. So here, that's not inside. Then, which is inside? How about bloodstream? Inside the bloodstream, is it inside? Relatively, that's a little further inside. And in medicine, actually, we use that terminology, exocrine and endocrine. Crine means secretion. Exo means to outside, and endo means to inside. Okay, so let's say pancreas, it generates the glucagon or insulin as a hormone, and those hormones are secreted into bloodstream, and those systems we call endocrine. So that means we count the blood inside the bloodstream. We count that as the inside. In comparison, if they generate digestive enzymes and they are secreted into this gastrointestinal pathway here, that is called as exocrine. That means we already count that this line here, these are kind of outside, we say. But that's a relative concept. The real inside should be inside the cell, isn't it? Cell is the basic unit of life. They have a cell membrane. Inside the cell versus outside of the cell, if you count that, inside the cell should be life space. Outside should be environment, isn't it? In the bloodstream, what do we have? We have leukocytes, we have red blood cells, we have cells. They are floating in the blood, right? Then, inside the blood system, the blood vessels, still there are cells in there, and blood area should be environment to those cells. That's not really inside. That's also kind of environmental area. Then if you think, oops, okay, here, something is missing here. Okay, I missed the one page. Okay, you have the table of, you don't have the table, but in the video you have the table, inside cell and outside cell of different concentration of ions, right? So let's try and reconstruct that page. Okay, in and out. Outside of the cells, a lot of sodium. 100 millimolar concentration of sodium. Inside of the cells, we have countering another ion here. What is it? Potassium. K plus. Almost similar concentrations. Keeping similar concentrations is important to keep osmotic pressure, osmotic balance. If there's too much ion in one side, then water is moving to that direction. That's a problem. Outside, there are a lot of chloride. Outside, they have a lot of calcium. Inside, very low calcium. But inside, there are a lot of phosphate. Now, looking at this is our environment, right? Environment, they have a lot of sodium chloride. There is a good evidence that our life started from seawater. Our blood, the composition is kind of a diluted seawater. And then to keep, in the beginning, maybe we make membrane structure. We try to pump out sodium to the outside. To keep that balance, we pump in selectively potassium to get the balance. And then accumulate what we need inside and pump out something we don't want to use. So this is the definition of in and out of those life forms. And then I put some questions about of whether virus is life or not. Very strong no, some of you said. Okay, this is quite the attacking sentences. If you have some other DNA, take out from the cells and package that into some protein, then would this protein DNA at the bubble is life? Yeah, of course it's not life. But this description is quite interesting description. This is the shape of a virus. Take out the DNA and then package that with some protein. This is like a virus. I'm saying this because all the cells, they have a cell membrane. Those cell membranes are composed of lipid bilayer. Virus, some of them they have a membrane, but many of those viruses, they do not have a membrane. They have a DNA or RNA as a genetic material. Outside is just a coat of a protein. It's kind of a capsid. So usually they don't call it the virus membrane, they call it virus coat. So this is like a virus. Some of you said yes, because if it goes into, in terms of this definition, it goes in blah blah blah, and then somehow it maintains itself and it induces replication, even though utilizing somebody else's machinery. Well, there is no fixed answer for this, but personally I believe viruses should be considered as life because it has a very close connection to our life systems. Even though those are fragmented DNA, small fragment of DNA, once they are inside our body, they participate very actively with life functions. They can get into our genome, our gene the system. They can make proteins exactly as we do. And that's kind of the fragment of small life forms. I think that's okay. That's my opinion. Anyway, there's no fixed answer for this, but those kind of particles, even synthetic cell or synthetic virus, they can be formed exactly similar way like this, synthesizing DNA or extracting those DNA and then package it somehow into protein or into liposome. Liposome is more similar to cell structure, right? With a lipid bilayer kind of structure. Okay. Okay, so at least today when we prepared for this lecture, TA and myself was a little struggled. Next class will be Tuesday. I'm ready to show you the next the online class. But let's change the assignment time a little earlier. Tuesday morning, too busy. I was so busy, she was so busy, and she gave me one material yesterday, another material today. Some part of them is overlapped, and I found some of your answers is in the last minute. You take one day shorter, but you put out your study, finish your study, and also put out those answers by the Monday morning. That we have one day of preparing for the classes. Okay, so that's fair enough. Anyway, I will make it available right away after this class. You will have 5-6 days of studying. So you study your material. The next part of study is structure of cells. And then utilizing this simple membrane model, how those complicated structure of cells is formed will be you will study. Any question so far? 아까 내가 어느 파트에서 다시 얘기하겠다고 그랬지? 시간이 남으면 요새 잊어버렸어. 그거 아니었는데 조금 더 앞에 혹시 시간이 모자랄까봐 지금 있는데 Which part did I say I will come back later if we have more time? Okay, this part. Okay, so now let's think about the relative thickness of our cell membrane comparing to soap bubble. Soap bubble, they say, this membrane with the water, they may have a 10 micrometer thickness, 10 micrometer, but when they reaches about 1 micrometer, they may rupture. So let's say 1 micrometer, and let's assume 10 centimeter the soap bubble with 1 micrometer size. So this is one model. Our cell, 10 micrometer size, and then 4 nanometer thickness. Relatively, which membrane is thinner or thicker? Comparing to soap bubble versus our cell membrane. Which is thicker, how many fold? Did you get the answer? Okay, seems like if you have a 10 micrometer, a little thicker soap bubble, then maybe the relative ratio is similar to each other. If it's a very thin layer, then this is much smaller. So let's think this one a little differently. If we amplify this into the bigger size, billion times, then this cell size becomes a 10 kilometer. 10 kilometer is approximately the size of a Guam city. 10 kilometer size of a city, and then let's say this membrane is city wall around. 4 nanometer is about 4 meter. Comparing to whole Guam city size, and then the cell membrane is only 4 meter, like this size. It's a relatively very thin layer covering that big area. In that scale, water molecule is about 30 centimeter, like this. So this kind of a boomerang is needed to penetrate from here to the other end over there. That's water molecules that travel across the membrane. Glucose molecule is about this size, very hydrophilic. It's hydrated carbon, 물질 잔뜩된 carbon. So that's why glucose cannot penetrate this. It's this size of a glucose. It needs to penetrate that much. This layer, the wall layer is not trivial layer. It's quite a big barrier. That's why, in many cases, we need this kind of transporters. Some transporters, there are two kinds of transporters. One is a pump, the other is a channel. This is a channel. Let's say this is carrier or pump. What can be the big difference between channel and pump, do you think? Energy. Which one requires energy? Pump requires energy. What is the energy source? ATP. Utilizing usually ATP. That's why we call ATP is a biological battery. Okay. So pump then is much slower. It should be done one by one by utilizing ATP. Channel, once it is open, then thousands of molecules passes through very quickly. That means the channel should be very carefully controlled. It's more efficient, but it can be also dangerous too. Right? So many of those toxins we have, or the chemical weapons, they attack usually these channels. Open it or block it. Then our the biological function can be damaged significantly. Okay, so this is the end of today's lecture. Any question so far? 그러면 수업은 없이 끝나기로 하고